Hey Dinesh.
Oh, hi. I thought you were not joining, so I joined
Yeah,
it.
I'm gonna skip to that. I just wanted to check that you have you're able to share your screen because I still can't figure out Zoom settings. Uh, so
Oh, okay. Okay. I'll try to share my screen right now. Just give me a second. Okay, you
yeah,
have disabled screen sharing. Yeah, you might need to enable it. It's showing me that it's
I
disabled.
don't know how to enable this permanently. I have to do this every time. Can you try now?
Okay. Yeah, it's now possible.
Okay,
Uh,
cool. Right, I'm gonna drop. Let me know if you need me. I'm around. I'm just gonna be on another call. I have to talk to some.
okay.
But
Okay. Cool.
good luck. Have a good one.
Cool.
Hello, Dinesh.
Hi, Samarth. Let's just wait for 1 or 2 more minutes.
Mhm.
I think that timings change have maybe that's why people are not here right now. Can you hear me, Samarth? I'll start.
Okay.
Okay, cool. So share my screen now.
So basically, this was the paper mainly by Google folks and some other, U of T and some other collaborators as well. So basically, what the main idea of this paper is, like, to begin with, is that it wants to say that we are not going to use recurrent neural network based representation that we have for encoder decoder, and we would go with like simple attention mechanisms, and we won't have any recurrent units like which used to forward their embeddings and output and hidden states to the other adjacent recurrent units. So that's the main goal, because we'll be going over why it's the main goal and how it's beneficial. And apart from that, it also tries to amplify what the concept of soft attention was trying to do, and use self attention as in place of that, and achieve a little better results. So in the initial abstract, so I'll be going line by line, I mean paragraph by paragraph, and
Mhm.
just mentioning the important aspects, and so that you have a little bit of concrete language as well, because maybe I'll be using some lingo and it might not be clear. So yeah, so as you can see that in the abstract there, the main idea is that the dominant transductions model. So basically transduction, as far as I could understand, is that basically something, some model which actually transforms into some other embeddings. So basically RNN tries to take in the words and convert them into some embeddings and hidden state and all those. So that's why they are called transduction models. So those models, like basically dominant transduction models, means which are performing really good, are based on recurrent or convolution neural networks, and they include encoder and decoders that we all know, right? But what it is trying to do is that it is trying to simplify the architecture by simply dispensing the recurrence and convolutions. So basically we'll see why it wants to do that. Now apart from that, there are some like results which are being told here, which I don't think is that much relevant right now. Maybe we can go over that in the end. So in the introduction, what they have like briefly told us is that you can see here that state of the art is actually achieved right now, like in 2017, whenever this paper came, by transduction models, which use sequence modeling and use those like gated recurrence and neural networks like RN and all those. So the main problem with them was that they did not scale. So, as it mentions in this paragraph, like they have computational bottlenecks. So like if they have a very long length of sequences, or maybe if they have large amount of weights, then the memory and the computation can become a bottleneck. Like we saw, like RNN has a lot of parameters. So it's easy to understand why computation can be a bottleneck.
Actually, not sure because RNNs are more efficient. It's just that their time, because they are recurrent, so they take more time. I think I mean, when you say computational bottleneck, if you mean like resources, then I think transformer or attention-based models that consume more memory and computational resources.
Yeah,
Then
I think I
RNN.
agree. Yeah, I think that there is one very important term to consider here is parallelization. So
Yeah.
what happens is that overall, yeah, transformer computationally can be worse. In fact, it is worse because I actually calculated time complexity of the model,
Yeah, it's
and
worse.
yeah, it's worse. But the thing is that it's parallelizable, and that's the reason I think it's, so that's the main component that I think that I should have
Yeah,
mentioned. Yeah, so the
Mhm.
sequential nature actually, it becomes critical at longer sequence length. So basically that's the reason. Maybe, yeah,
Yeah.
because weights are more in like transformers, but yeah, because it's parallelizable. But there is like this is one line that I want to just mention. This is not related to computation, but this is
Mhm.
good because this tells that RNNs take along the symbol positions for input and output sequences. So that's an issue with transformers, and how they solve it, it would be later discussed.
Actually, this is a strength, I would say, of RNNs.
Yeah.
So positional information, and if you look in the paper, I think you mentioned, right, CNNs versus RNN based models. So the problem with, I believe, I mean, I know that with RNN was on the training time, because it's recurrent, it takes it has to wait for the previous time step to complete before it can compute the current time step. So
Exactly.
this problem was solved in a way. If you remember the convolution architecture that we discussed before. So convolution you can do in parallel. They were super fast.
Yeah. We'll compare them with transformers as well. How convolution does
But
something parallelly, but where they lack. So they
okay.
compare. Yeah. So sorry,
Mhm.
I was about to sneeze. Sorry. Yeah, it's okay now.
No
So,
problem. Natural
aligning the
that's
yeah. So the aligning positions steps in computation
Mhm.
generate sequences of hidden state as a function of an input of position T. So this is
Mhm.
the strengths of
Yeah.
RNN, and this is something that they will try to model in transformers as
Yes.
well.
Yes.
So, uh, so there is just a going mention of some improvements like parallelization kind of stuff. I mean, they have introduced some sort of factorization in weights and some sort of model performance improvement, like they have mentioned some papers. So what they are trying to do is doing some sort of decomposition of matrices in these papers, and then they are trying to speed up because of smaller matrix multiplication and all those stuff.
Mhm.
So that's the idea here.
So essentially
So
dimensionality reduction and then performing because the
yeah,
matrix sizes goes down.
yeah, this is the general essence.
Mhm.
Details can be gone through. So apart from this, so now coming back to attention mechanisms and transformers. So what they essentially are trying to do is, like, for broader people, so they're trying to model some sort of dependencies without regard to the distances. So that's the like main
Mhm.
catch here, that they try to model relationships, and it does not need to be close or it does not need to be separate. Everything is equal for it. And then what it says is that in some cases, like we have seen soft attention, like it is being used in in conjunction with recurrent networks. So that is also a good use case and good implementation. But transformer is something else. So they just mention that soft tension is not specific to transformers. So, and now what they're trying to say is that they have completely removed recurrence, and they draw global dependencies from input and output and all those stuff, like again, like parallelization, state of the art, translation quality. So yeah. Now coming back to a little background. So basically in this, I would like to focus on the fact that, sequential computation reduction. So basically it's a known problem, and there has been some sort of like proposed architectures, ByteNet and Com2S. I think I've heard somewhere in machine translation related to ByteNet, but I've not gone through the details. But yeah, this is used in if it is used in machine translation, I think it should be doing good. Really, it should have great performance and all those. So in this, as you can see, that it's mentioned that convolution neural networks as a building block and computing hidden representation in parallel for all inputs. So like you mentioned right now, like convolution neural networks can do parallelly. So these was one of the speed up that they tried to achieve. But they mentioned that the number of operations required to relate signal grow as the distance between positions increase for conn2s and logarithmically for ByteNet. So this was one of the problem with like convolutional neural networks, like the relationship between distant data points can be linearly in time. I mean, it's not if you try to access it using the convolutional architecture in its very like generic form, or you can say without any tweaks, it is usually linear. Like if you try to access the feature which is like at the end of the output layer of the kernel. So that's the idea. This is important. Let me know if not clear, because it will maybe we can skip this for later if it's not that clear. But yeah, if there's any quick question, we can go over that.
I think it's more of the problem with the Conv architecture, at least from what I understood, is they are good in parallel, but the basic problem is they lose the positional information.
Yeah, I mean,
Because
if you try to incorporate that, then you will have a cost of
then it's
linearity.
a linearity cost, exactly. So if you kind of get in, somehow bake it into the actual conv operations, then you have to wait for that positional information to come into and factor it. So it kind of slows you down. Yes.
Exactly.
But
Exactly.
but positional was the killer. Not encoding the positional information was what brought down convolutional networks.
So the thing is, this is a little bit off topic, but I think that convolutional neural networks are more suited and were developed, I think, initially for image tasks, image based tasks. So I think in that positional like was less important, because usually object.
No. Position is important. Let's say if you marry con with attention, then they can take care of the positional. Spatial information is your positional information in images. So in a way, they could identify.
I mean, like I understand what you're trying to say, but I was just thinking abstractly, like if there is an object which needs to be recognized, it's going to be nearer, like its components are going to be nearer to it, because maybe an image is a like if you consider, like if you look at your left hand side, the objects and the image which would be shown would be nearer to the the main, let's say, centroid pixel. So that was my assumption, but yeah, definitely marrying it with transformer are going to give them more power. Okay, so what they are trying to say is now that they have reduced the number of operations for relating it to the far end or near end, but they have the cost of reduced resolution. So resolution is something I'm not sure in what sense they have used it, but to me, I could get that resolution of like by resolution they mean the activation as compared to others. For example, if it's trying to say that this is an adjective, let's say, so the resolution of adjective mean that the strength or the activation with which it want to say that they are related, like maybe that verb adjective relation and all those. So if the transformer is trying to say with a higher resolution, it might mean that it's trying to say with a higher activation. So that gets reduced if this something is not done in a normal simple single head attention, you can say transformer. So apart from this, there are like two architectures mentioned here. They are very esoteric, but I would just briefly mention that there are two terms in that, which are recurrent attention mechanisms and sequence aligned RNNs. So recurrent attention mechanisms, I'll just briefly mention it's something related to attention. And what they're trying to do essentially is, maybe if I have any image, yeah, this is something what they're trying to do. They take in all the sentences, they take the question query, then they have some embeddings, they convert to some, and what they're essentially trying to do is to take up all the sentence together, and that's how they are trying to mimic the attention.
So this is
that they
memory
can.
network, right? This is architecture for memory network.
Yeah. So they are referring to end-to-end memory networks only, as they are based on recurrent attention mechanisms.
Yes.
So yeah. So I think you know about it. Maybe you can correct me if I'm wrong. So what I understood is that they're trying to do something, a simpler form of attention, and they just take up all the sentences and have a query, and then they do some projection, and then they use that projection matrix to do some weighted average, and then they produce the output, which is a very simple process. It's just that they're taking all the sentences together and projecting it with the embedding B. So that's how I think they're trying to say that they perform well on simple language question answering, because they are, I think, pretty efficient and might be able to learn easily.
So
So
there, one thing here is in memory network, just a small thing. If you look at the picture, there are two parts. One is the left-hand side of the question where they are just mixing. You can think of it like looking at the same sentence words and mixing and matching them, which is the left-hand side. The main strength of memory and network was is that they, like, if you look at RNN, that is also a kind of a memory network, but it
yeah.
stores only one vector in its memory cell. Versus here, what they did is they kind of created a bigger memory place, and then they did, and whenever a query comes or question comes, they try to see which memory cell using attention, like the blue and what you see here, blue and orange boxes on the right. They go there and then try to find out. So this was I mean, this is a very good architecture if you want to keep, like, if you have less load and you want to retain some memory in the system, independent of anything. I mean, in the task, it's a general kind of architecture where you can leverage these
Yeah,
memory
exactly.
slots.
This is pretty simple and can be, I think, applied many ways. So maybe the simplicity is, that's why it can be applied many ways. So moving on, I would just mention small like references, sequence aligned RNNs and convolution. They have mentioned that this is transformer is the first transaction model. And so this is an interesting term, sequence aligned RNNs. I think everybody knows it, but just wanted to mention sequence aligned RNNs have been compared here and mentioned here. Maybe you guys can later on visit it. So moving on to the architecture now. So it mentioned that like transformer is going to have encoder decoder structures. So like every other architecture, and in that encoder decoder we'll go over that, but before that it just mentioned that like after encoder and decoder sub layers, it's had 0.5 fully connected layers. So this is just like a normal, convolutional layer. So like it mentioned in the paper later on that it behaves like a convolutional layer. So you can think of like when you get some representation, you are doing a convolution to extract some features. Just a small lightweight, but yeah, doing something like convolution. Just wanted to mention here. So now coming to encoder and decoder structure. So I won't be going on to the numbers exactly like the stack n is equal to 6. I will just go over the basic architecture. So, and I would like start with this image first. So what, as you can see, like this, the left side is the encoder and this the right side is the decoder. So it's there are multiple encoders. There would be for multiple sequence. So like it's not shown here, but that can be assumed. And what's the fundamental parts of the encoder are that the first sublayer, it contains a multi-head attention, and then it has an add and norm. So we'll go over what multi-head attention and add and norm layers are. But I'd just like to mention here a quick side note that it has this arrow. So I was a little confused why it has this little arrow. And I think I asked in last Sunday that why is there. So I just got to know that this is something related to residual networks and
Yeah.
ResNets. So maybe I'm not going to go detail into that, but yeah, this is related to residual and it helps in learning. Similarly, there are add and norms. Normalization is also some sort of trick which is used for maybe help in learning, and
Add and norm is nothing doing nothing, but if you look the multi-head attention output and the residual output, you need to add them together. So that's the addition part to come up with one vector as output. So you're getting two inputs to add and norm. So add layer does the addition and normalization is that normalizer. So that's
yeah,
what
there's
add
this
and
very simple here, but just the fact that normalization, they mentioned that normalization in, they mentioned that specifically that it's actually done with some following reference. So I just thought that I should go over it because maybe normalization is something important technique. So normalization is done to, just normalize all the activations so that no one
Yeah.
activation is overpowering some other.
Yeah, yeah. If you
This is
have
a very,
heard batch normalization, that's what essentially.
yeah. And the top layer is the pointwise feed forward layer that we discussed. It also has a residual connection, and then this output along with the other encoders output. This is not shown here, but this, like, I have came across and understood that actually not just this, multiple encoder outputs are actually going here in the
Yeah.
decoder section. So this
So
is
if you
really
look,
important.
yeah, if you look this n times on the left side, n cross is looking right on your encoder diagram leftmost.
Yeah, definitely. And so basically the encoder representation, let's just assume strictly that they produce some vector embeddings. So there are two things that the decoder will do. We'll go over that, but you can see there are two arrows for that reason. So just wanted to mention, it's really interesting that they have, not given straight away what they mean by two arrows, but yeah. So so this was the encoder basic. I'm not going to multi-head. We'll go over that quickly. So apart from this, let's go over decoder, then we'll go over multi-head attention. So as you can see, the decoder has the same multi-head attention layer, add norm, and feed forward, and all those. They have positional encoding. We'll go over that. So now coming to multi-head attention. So we'll come back to decoder once they have something interesting. So what the multi-head attention is trying to do, and in general attention is trying to do, is like they have this query key and value concept. So for this, I think it's best to have some sort of better visualization, which I think I've lost it, the link. But yeah, so it was in the textbook book as well, like how key and queries are related. So what essentially is attention trying to do is like it takes up, let's say, the input, the main positional character as a query, and consider all other sequence character or words as the keys. And then what it tries to do is like for attention, self-attention, the general concept is that you give in a query and it tries to match and it tries to do some mathematical with all the keys present and gives you an output as the value. So I'll just come up with that, model which is in the book, so that it's maybe if someone sees this video, it would be really easy. Mm, hmm. Yeah, so this is the idea of self-attention, and this is very easy to scale to multi-head attention once we are clear with this. So what essentially is happening is that when we have, let's say, x3 as the input word, and then we want to have, some sort of relation with all other input words in the sequence, then we consider this as the query. So we want to, query that how x3 is related to all other words. So that's why you can think like this query, and then all other are the keys to which it can be related. So how it is done, like the embeddings of each word is there first multiplied to form the key embeddings of each, and then using the embeddings of the query word, we are going to just do a dot product for self-attention in transformers. So basically there are three sort of weights. First is the query weight, like it's mentioned here, WQ. Then there is key weight, and then there is value weight. So these three weights are actually learned, and so basically that's, let's say it's learned right now, and we are trying to do some sort of like decoding, or you can say maybe we just doing one step. So in that case, what we are trying to do is that, again, I'll repeat that we, let's say for the word x3, we are want to query how is it related to all other. In that we multiply it with the query weight, and then we multiply the embeddings with the keys which are produced using the WK weights, and then they pass through softmax layer, and each, like, you can think of like this would give you, after dot product, row vector or column vector, and then you do a softmax over it, and then when you like are done with the softmax, you just multiply the value of each with the weight, and then finally give the output. So this is like attention. Self-attention is nothing but just a query and output mechanism, and inside the black box can be anything. So the query right now in transformers language model would be how x3 is related to other words. So the relation can be of different sort. I mean, numerically it might not make sense, but yeah, understanding of the model might lead to that it's related somehow in adjective or verb form and all those stuff. So that's the idea of self-attention. So how multi-head is done, now coming to this. So we can assume that the VKQ weights matrices um, are single, like I think I mentioned it somewhere in the channel as well. So what the model will learn is like they will learn the projection of these into different like heads. So I just shown that there are three heads parallel. So you can see that they are going behind. So these are three parallel heads. So it might be of lower dimension. So this won't increase the computational complexity, and learning would be easily as well. So, but the benefit is that, like I mentioned in the earlier starting phase, that granularity and resolution is lost because it tries to, does averaging softmax, like I mentioned. So basically, so because of all those stuff, if we have multi-head, then we can capture different relations, and we won't be doing that at the expense of some other relation. So that's very important with multi-head. But the thing is that we'll come over this scale dot product. We need to do like concatenation and some massaging, because essentially it might be like the dimension would not match. So those are important thing to be keep in mind. Okay, so this was about the multi-head. So now the scale dot product. So what happens is that when we do dot product, so there are two ways of, the paper mention talks about two ways of doing query key multiplication. So basically finding similarity in query key. So the two ways are, first is simple dot product. The other is having a, they call it additive attention. I think the two most commonly used attention functions are additive and the dot product. So yeah, it's the additive attention. The term is additive attention. So it's nothing but somewhat on feed-forward neural network based with one single hidden layer they have mentioned. And what it does is that it is almost similar in performance in every aspect, but just that there are optimization around matrix multiplication in nowadays. So that's why they have chosen dot product. So the problem with dot, they had in fact problems with dot product. That is the like values of dot product can increase really high and can cause overflow. So for that, what they're trying to do is that matrix multiplication is done and then they are scaling that. So they are using a factor of root d. D is a dimension of the model of the internal representation. And then they're doing some masking, which is for decoder side. This is optional, that's why they have shown. And then they are doing softmax. So this scaling is done to just keep the values in check so that gradients does not explode. So that's the idea of scaling dot product. So that's the basic idea. Now coming back to decoder, there's one important thing that's happening in decoder I wanted to mention is that they're doing in the decoder, they are doing this multi-head attention. This is at first not clear from the diagram why it's like, I mean, they have used the term encoder decoder attention, but it's not clear from the diagram where is it. So I just wanted to mention that encoder decoder attention is actually this part where there is multi-head attention and in the decoder side. And what it does is that this is pretty interesting what they've done. Like they have suggested to use the output of all the outputs of the encoders as the input for the key and the value, whereas the output of the previous decoders, if we are doing language modeling, as an input for the query. So essentially, if we have, let's say, simple language modeling task, and let's say we are doing a translation, in that case, let's say we have a sentence of, hi, this is a sunny day. So if the output has produced, let's say, two words in translated, let's say Spanish. So like whatever the hi is like in Spanish, and they do that, and then they are going to produce the second word. So in that case, what they're trying to do is they're trying to take input of the decoder till that stage t-1 as a for the query. So it makes sense because it's like, what's the query? What's my t is equal to 2 word? So it's some sort of a query. So, but it has some sort of attention like what I have already produced. So that's why it's like in the t is equal to 2 query. And then encoders output are used for key and value. So this can be understood. So basically, it's another term for encoder decoder attention is cross attention. So what they do is that they take up the encoder's output and have weights like multi-head weights K and WK and WV, which would be then multiplied to the encoder outputs, and then they would produce the K and V matrices, and the Q would be from the output of the previous decoders with the masking as well. So now we have all K, Q, and V, and then it is used. So KQ again, so KV, I would again mention that it's from the encoder. So this can be understood like while we are trying to produce the next word, we are querying the already outputted sentence, but we are getting the information of keys and how to produce the value from the encoders. So it's like it's giving me the semantics of the sentence, and the query is giving me what till I have produced. So that's something that they're doing in cross attention.
I think simplest way to visualize this is your encoder is your, let's say you're doing the translation, right? So your encoder output, which is coming in the decoder, is some kind of a representation of your input sentence.
Yeah, the semantics
English.
and all those. Yeah.
Yeah. So this is, let's say, just a vector of your hi, this is a sunny day in English. So these you're transforming them into keys and values, but because you need to convert it into Spanish, you need a query from Spanish. So till after multi-head mask attention, this is, you can think of local effect, the first below block, and then you get it into saying now which a representation of the Spanish thing, and now you say okay, which what words or what aspects of the input vectors of input sentence are should I pay attention to for my incoming Spanish sentence, or which words in the Spanish sentence should be aligned to words in the English sentence. So that's what
Exactly.
That's
exactly.
simple. That's what is happening here.
Yeah. So this is really like I think this was the most interesting part for me in the decoders, like how they actually take in the query from the till now generated Spanish sentence, and they are querying it to the semantics and the meaning and the senses, all those representation learned in the encoder, and they are generating the output. So this is the meat of, I think, transformers, how they combine all these self-attention and all those here in the cross attention. And yeah, like somewhat mentioned that it's masked multi-head attention. So masked in the sense, like, I don't know, maybe you guys have already read about it, but we usually tend to put minus infinity in the t greater than the current decoding word, because still decoding is still going to be sequential. So that's why it's going to be masked in the t greater than the current word.
I think the main problem, the main reason mask was brought into the game, I don't know, do you know, Dinesh, why mask was brought into this?
Like
this
for
entire-
language modeling and for translation, it seemed to be following the same reason like we do in RNNs and all those. And for birds, like masking is, I think, a little different. So
No, but
if you're
what is the reason for masking? Maybe, I'm just asking because I know a reason, maybe that's incorrect. What
okay,
you
so
might have researched.
I think that the value setting to minus infinity makes sense because, like, if you do softmax over minus infinity is going to produce 0, and
Yeah.
eventually there won't be any
No,
weights
but
added.
that's a technical reasoning,
Yeah.
right? What was the
Yeah.
intuitive reasoning? Why do you need masking in the first place?
So this is, I mean, I would say there are two reasons. I don't know how valid they would be. Like, first one is that you do not want to model why would you run a model if you know the output of the futures and of the current word and the future word, because the future word is going to be current word that need to be guessed. So then there won't be any need if you already have that future word. And then second is usually sentences or the languages are left to right. So a human, what he or she does is like in the left to right languages, it tries to come up with the word which is like already have written, then it comes with the word, then it comes with the word, then it comes with the word. That's how human does. So that's maybe the second reason I have. That's a very like layman, but yeah.
Okay. I mean, I know about the first one, what you said exactly. That's what I think. So essentially, if you, in the training process during the decoder, if you give, let's say, the entire translation in one go, in a way, you're cheating.
Yeah.
So that's why you mask the words. So, but there's at one time you need to, it's not, you don't want to do things sequentially. You want to still leverage the power of parallelism. So, but
So yeah,
inherently things are sequential, like you said. Inherently things are sequential. So the way out is you mask everything from the future that you want, assuming in a way you are pretending that you have not seen the words, and then you move forward.
yes. So coming back to our paper, so in this it mentions that it does multi-head attention over the output of the encoder stack, like I just mentioned. Samarth also mentioned few points. They should be helpful. Then here's some important text I would like to mention is that this the same like masking one, like it to prevent position from attending to subsequent, and offsetting that prediction can only depend on the known output, like we were discussing. So this is all about the encoder decoder architecture. So now I would go quickly because I think these topics I have covered. So like mapping a query and a set of key value to an output, like I mentioned, this is the basic definition of attention. Anyone can just learn by heart this. And where the weight assigned to each value is computed compatibility function of the query with the, like I mentioned, we can think of this as a black box. We can have either dot products or we can have either feed forward, like additive attention, like I just mentioned, can be done via neural networks. So jumping ahead,
There is one question here on the key, query and the key, the vectors assignment. Is it just a random assignment, or there are some approaches as well to decide the initial, the initialization?
so
Initial
there
values
are,
of this.
so you're trying to talk about the weights, WK, WQ, and WV.
Yeah, the query and the key.
So there are two things. Initially, we have word embeddings. Those word embeddings are maybe learned by a Word2Vec, BERT, or maybe anything. Then we have this weight vectors where we project to the internal representation for key, query, and value. These weights are actually learned. WK, WQ, WV are actually learned. Now about initialization, I have not seen anything mentioned in this paper regarding proper initialization. These are learned parameters. These won't be hyperparameters. So I don't think that there should be any reason to set to some values, because if we are learning, then we should have more focus on gradients. But yeah, there are some, I think, conditions in which it can lead to better results, because we may start at a better local minimum, a better point in the gradient. But in this paper, Rahul, I've not seen anything regarding your question. So yeah.
Got it. Thank you.
So going to multi-head attention, so basically it mentions that linear projection of the key with different learn projection. Like I mentioned that initially they have the same VKQ for a single transformer unit, transformer block. Then they do projection over different heads. They call them heads, and you can just simply call them any any word you want. But what they are essentially trying to do is trying to capture different relationships with a little bit more granularity. So that's what they have mentioned. Attention allows to model jointly information from different subspaces, which is like a simplification, I would say, different features, and with a single attention head, averaging inhibits this. So averaging is going to happen because if you are trying to think about if you're trying to have multiple feature learning at the same time with the same weights, then somehow some feature might get averaged out, might get neglected. So in that sense, it would be. They've mentioned about the dimensions of the multi-heads, and what was the factor they have done. They have reduced by 8, I think. So yeah. Now coming back to encoder decoder attention layer, it's not I just give a brief what's the encoder decoder cross attention layers and all those. So this is a very important line. I think I have mentioned this, but yeah, we can just go over quickly. This allows every position in the decoder to attend over all the position and input sequence because it takes in all the inputs from the encoder. And this mimics the typical RNN mechanism for seek-to-seek models, because in that also they have hidden state that comes from the last encoder unit, and it has all the input encoder information. Then the encoder has self-attention layer, which can listen to all the positions in the previous layer. So the previous layer can be the simply word embeddings as well. And we can stack on the top of one encoder, another encoder, just like we do in RNN. We can have different heights of encoder, not just depth wise, height wise as well. So in the self-attention layer, the decoder allows each position to attend all position up to including that position, like we mentioned. Now, coming back to the important thing in this section, point-wise feed-forward networks, I mentioned briefly in the beginning, point-wise feed-forward networks are trying to do some sort of convolution with kernel size 1. This is very clearly mentioned here. I think this is enough to say about it. It tries to extract some more features out of the representation, and it has a inner layer dimensionality of 2048. So it's definitely going to do some sort of encoder decoder again and autoencoder type of stuff, and going to give a little bit more information. Then we can go to embeddings and softmax. It is a very small thing. What they're trying to say is it's just for the output words. What they're trying to do is they're having embedding matrices. So like I mentioned, they can be using BERT, Word2Vec, anything, or maybe embedding metrics. They can learn that as well. That's not an issue. But the thing is they have done some sort of multiplication with the weights through D model. So this is not clear to me why they have done that. They have not mentioned it clearly, but yeah, it should be related to learning as well, like we do root DK in the scaled dot product. Then we have positional encoding. Positional encoding is something important. Glad we have time to look at it. So in positional encoding, every even positional word is given this sinusoid multiplication, and every odd position word is given this sinusoid multiplication. So if you compute the wavelength of the sinusoid for positions, it would vary from 2 pi to 10,000 pi. So the benefit of this will talk about I think there are they have mentioned that they have done positional encoding using learned positional encodings. So but it gained the same result, but what they did is that they still went ahead with sinusoidal wave because they felt that it could maybe extrapolate to sequence length longer than the encountered during training. So maybe in testing they are expecting in future they might find some point where it's better. So yeah, it's their call. So coming back to sinusoidal embeddings, what they're trying to do is essentially that this is their main, you can say the, reason for doing this. So if you have read about sinusoid, you can have repetition in sinusoid, and if you do like positional embedding, position plus k, then you can relate it to the positional embedding of the position. So if think about it, like if there is sentence in which there is a word at, let's say I is equal to 2, and let's say at I is equal to 4, then if they are somehow related, then this method is going to, like sinusoid is going to easily capture that. But then there is some like there is some, definitely you can say, I'm not sure, I've not done the math around it, but maybe there can be some cases where it's become too much of you can say sinusoids which are going to give one, so it might affect the performance, or you can say the outputs of the embeddings. Now coming back to their findings and their reason for using self-attention and why they recommend. So one is that they want to reduce the total complexity per layer. So this is very important, per layer. And what they have done is they have shown this table, and this is per layer table. This is not the overall complexity of the transformer model. This is a very good view. Transformer model are worse in time complexity as compared to recurrent as well. So now consider the fact that n is always going to be smaller than d. So because n is going to the input length sequence, and d is the representation, and k is the kernel size of the convolution. I won't go over the other, I would just go over self-attention. So you can just simply think of this self-attention as n squared d, because each word is going to relate it to the other word, that's going to give n square, and it's going to relate using a dot product, so that's why n squared d. This is a very simple, I would like to give brief. Now coming to the amount of computation that can be parallelized, as we mentioned, it's really huge. That's really great. And the third point is that the distance between the long range impedancy. I think this was something mentioned by Samarth as well in the beginning. So what the maximum path length is O1, because there is n square, you can say, full, it's like a fully connected. So if you have a fully connected, then it's going to have only a, O1 path. Whereas in convolution, if you do a convolution, the output layer can have distance of log kn. I won't go over the maths, but just understand like it's going to be distant apart. But you can just do the maths. I did it, and it's like this right amount. So there's the last paragraph which is important. Apart from these, everything is numbers. Conceptually, they want to say that self-attention can yield more interpretable models, and we inspect attention distribution from under and present, discuss example. In not only do individual attention had clearly learned to perform different tasks, many appears to exhibit behavior related to the syntactic and semantic structure of the sentences. This is, I think, the conclusion you can say. Apart from this, everything is just numbers. I won't go over them. So I think this is it from my side. I think I covered it within time. So yeah, any questions?
So Rahul, sorry, Dinesh, do you have that attention map picture anywhere? Generally, do they mention this in the paper?
I think it is not mentioned in the paper. It might be on the GitHub that they have given.
Because that's a very intuitive thing. What happens in the model?
Yeah. I think, I mean, actually the thing is that I used to get, I think it should be on this GitHub, I think. I've seen it somewhere. It's might be, drilled down. So you can quickly search over in every transformer article. Now I just found that, so I can just.
Yeah, that's this transformers attention maps.
This had it, I think. Yeah, this one, right?
sorry, yes, this is one, but I think there's a matrix. Sometimes people show that matrix. It's very, very, very intuitive. As in what is firing with what.
Okay, I think that I think I've not seen that, but I could form intuition using, you know, this as well. So if this really helps, like what it is trying to do is like it's trying to, you know, find the like relationship with all the other keys, and the one which are highlighted, like the green, is some sort of relation. It may be the referential, like the tire, like, so the tire is what is being referred with the it. So maybe that's how they are trying to do, as far as I remember. So the one which is the highlighted one, and the relationship represented by the color, and the highlighted one is the most related one. Similarly with the orange head, you can say. I think that's what it tries to say somewhat. You can maybe.
Yeah, actually, that's. I mean, if you put this in a matrix with just one attention head, then you'll see a very beautiful picture, and which is like you can quickly connect to it.
Maybe you can share
Right.
me the link if you have it handy.
Yeah, I'll
You can share it on the chat. I'll just pop it up. And
yeah, I think this one is good. I mean, there are many, but I think this one is really good. Yeah, I've shared it on the chat. So if you scroll down in that paper at the bottom, yeah, those grids, yeah, these grids that you see. So this is the kind of grids you can imagine which will come, and which ones are kind of giving you. So if you scroll up, I think somewhere they have it. This is a good example. I mean, so if you see, this is, I think, from okay, this is self-attention what is being shown here. But if imagine if it's a translation thing, then on the rows you could have French or another source language, and on the columns you can have what's the words, corresponding words or translation in the target language. And these squares, what you see, if you project or if you visualize the attention weights that the model after learning gives, then you'll see that, oh, actually carousel is one word related to 5 words in French, or one French word relates to 6 words in English. So that's what this grid will show you.
Yeah, like the in the output is being related to person, like it's the quantifier for the person, and on is like again related to person because a person on a boat, like it's, I don't know.
Yeah, so
On
this
a
is
boat.
showing you some kind of maybe a semantic or syntactic structure relationship.
Okay.
So what the weights these attention weights learn depends on different heads, right? What you saw. So some heads might learn about your syntactic structure. Some heads might learn about semantic structure.
Yeah.
So those weights, when you plot like this is a very, very good interpretation of what the model has learned, and you can say very nicely.
Yeah. I mean, the darkness represent the activations and
strength.
more.
More weight, attention weight. This is your attention weight.
Yes, definitely. I've seen this somewhere. Yeah. I think it's, I mean, it's like this similarly, that was also like, really, for me, it's really beneficial doing that as well, because if you look at the encoder side, like it's with encoder and decoder. So like if you look just at the encoder, then that is like is also one of the really great representation, where encoder side, it was related to, the tire and all those. So yeah, I mean, both are definitely helpful. So anybody can have a look at them later on. Any question, guys? Is it like everything was clear? Right.
I have few questions, but I think we are over time. Maybe I can ask next time, or if you don't want, if you don't mind
it's,
saying.
yeah, I have 5 minutes. You can go ahead, definitely. If it's an interesting question, then it's a bonus. So yeah.
What I was just trying to visualize about the architecture, right? In sec to sec, we talk about different kind of architectures. We have one to many, many to one, right? One to one. So how does that fit into this attention-based models? Do we still have all those, kind of the translation?
So machine translation with was not the scope for this paper, but like in general, what I've understood from machine translation and alignments, like we need some sort of like training data, which is very like carved out like that for translation perspectives. And if that is done properly, then I think any model can be employed. So translation is right now more problematic because of the word alignments, what I've understand, and phrase alignments and all those, because the text corpora, parallel text that we usually have, do not have alignments done. And if we try to teach and we try to train that, then it's going to be a difficult, like accuracy is not there, because again, then there is not even any semi-supervised way right now to do that, as far as I know, as far as I read, and no self-supervised as well. So I think machine translation can be done with the proper input at the data side. So you can think for transformer, if you have so basically in the transformer model, in the decoder side, when we do that training, we feed in the maybe cross entropy or maybe any sort of loss function with respect to the output. But again, if only we have the alignments, then only we'd be able to produce the error. So if that clarifies anything. I'm
No,
not an expert.
this kind of make sense. And the scenarios we get, right? We have in a sentence, right? There can be a different kind of relationship between the input and the output, and model will automatically learn those relationships. That can be a one-to-many translation.
Okay, I see. So I think we need to somehow like find the length of the output that we are going to generate, and let's say we keep it twice the length of the input that can be generated. Like in one-to-many, as you mentioned, there can be more than words that are actually the input encoder. So then in that case, maybe we can have one-to-many. And in case of like extra decoders, in that case, maybe would be producing like after end of sentence, they would be producing some sort of stuff which is not important. So that's one stab of mine on that architecture, but I've not done this by my hand. So maybe someone else can add. This is one, just my perspective.
Yeah, so there you can think of, if you encoder decoder is a generic setup. It's nothing specific to these guys. So imagine if you have to do image captioning. right? So in image captioning, what will be the encoder and what would be the decoder? The encoder will be what kind of model? A CNN based model,
Mhm.
because you'll feed in as input an image, you'll make it run through a CNN based model, and you'll get a vector representation for
Vector
your
representation.
for
Yeah.
your image. Right?
Image.
So
Yeah. Yeah.
that's your encoder, and then you feed it to a decoder. That you feed in that image vector to a decoder, which will be a, you can think of it like you can take now the transformer decoder layer, and instead of the arrows that were going, that multi-head arrows that were going in the decoder, you can think of those as multi-head arrows of your image, and that becomes your encoder decoder for your image caption.
Yeah. I mean, I think Samarth is adding to my point. Like we can have like any number of mappings. It doesn't matter. Like image does not have any word. So in that case, Rahul, I think we can have any number of outputs. That's not an issue. Many to one, one to many.
Yeah, so it's all how you map what is your encoder and what is your decoder and how you represent it.
In fact, to Rahul's point, I just remember that GPT-3 involves transformers, and you can do auto-generative summarization and all those. So in that case, you have a lot of length. In terms of length, there are a lot of transformer blocks going to be implied for that purpose. So you can think.
BERT has so the layers, that the slices that you see in the BERT architecture, those are nothing but transformers.
Exactly. So there can be like a lot number of transformers, and because of parallelization, there's no hamper.
But one thing is, if you are using it, I mean, at least that's what I have seen. It's always rosy. They say parallelization and all those things. But in practical, if you read, it took them, I don't know how many hours of time to train a model.
Yeah, they have mentioned it. So they did it in, they have mentioned state-of-the-art blue score of 41 after training of 3.5 days on 8 GPUs.
On 8 GPUs. So it becomes even bigger and bigger, the trainings and the computational resource requirement. Though it's running in parallel, it's huge. So yeah, it's not an architecture that we can, I mean, you can essentially, you can use this architecture for any other task apart from language also. Nobody stops you. I mean, you can, if you can map it to the right components, you can do it. But the challenge is this kind of a computational requirement, like GPUs and other things. If you don't have them, then this will bring you down, versus if you have, let's say, smaller GPU and number of GPUs and other things, then CNNs and traditional methods will work. It's just that it will take a little more time, but maybe that's okay for your problem setup.
I think these transformer like BERT, using BERT. So these are like if it does good, then it can represent a really starter and then fine tuning type of stuff. So if it does help in that, increasing accuracy using like like in your pipeline, the first step, which is always like you have it and you just need to fine tune it, like transfer learning, then I think these are really strong, because if you can improve accuracy from transfer learning to that extent, I think these are really, because they just run for once and you're gonna transfer it in every other task. So maybe that's one benefit of it.
So there's a catch, I think, there in that statement, as it's a true statement in general sense, but let's say these models are generated on what kind of text? They are generated on normal, like Wikipedia, news articles. Those are the things in which these are trained on and generated. Now, let's say in your organization, you have completely your own vocabulary.
Yeah,
Right.
yeah, definitely. Fine tuning, I think, is done for that purpose only, right? Task specific.
Yeah, even in task specific. So if you take your, let's say, BERT level, you have your own corpus, which is very specific to your work. Let's say these models are trained on English vocabulary, right? But let's say if you have Hindi news articles, or even if it is English, it's very specific to your proprietary. Let's say you are a Slack person or Slack organization or Salesforce kind of organization, then you will have, and you have your own help related documents or customer support documents. The vocabulary that you'll have will not match with these models on which you are trained. So when you are, even though you use these representations as an initial starting point, they may be better than using Glove or Word2Vec. But the computational cost to just generate that representation is high. So you can do that experiment. It was interesting. I did that. So for one of my tasks, I gave a sentence. I have a pre-trained BERT model, and I gave a sentence to it to generate the embedding, and it took hell lot of time on a CPU. Mind you, on a CPU. If you do it on a GPU, probably it will be quicker. So it needs GPUs. That's what my thing is, and you cannot run it just on simple tasks.
Yeah, and yeah, this makes sense. And one of the things that you mentioned, Samarth, about non-NLP related tasks, I know we are very focused on a NLP side, but I also wanted to learn, excuse me, how exactly do you use, let's say, attention-based models on non-NLP task?
I mean, the key idea there is what is your task, how you model encoder, decoder, what is the thing that you want to pay attention to. So it's a common generic architecture. Attention is a generic architecture.
I would like to hijack that and just, mention
Sure.
here that the output is weighted sum of value, which assigned to this computed compatibility function of the query with the corresponding key. So you can have any compatibility function you want, depending upon the task. They define attention just as a function mapping a query and a set of key value pairs to an output. So it's a very generic. They don't even define any NLP word here. So you can get that.
I can
the
also
term the thing, sorry to interrupt. So the thing I wanted to learn, even the data preparation side, how exactly people use it for the non-NLP task. Because I don't come from that background, and it is sometimes hard for me to visualize, the preparation. Here if I take an example, I was going over for the attention-based model, right? We prepare the embeddings, and then we have the models, and then we define the model architecture and go through that the whole process, right? But if it is a non-NLP task, the thought process and the explanation I wanted to learn.
Yeah, so it how do I say, there it's, for example, give me an example of a task, then probably that's easy.
Okay, so let's say you are trying to predict a customer satisfaction score, some sort of CSP, and you have n number of just the numbers, right? You have n number of variables. Maybe customer, while doing the survey, those metrics are gathered. Maybe 100 different metrics are there. Now over that, we are trying to get the CSP 1 out of 1 to 10, right? That is the range over the multiple metrics which are gathered as a part of the survey, and we want to use the attention-based, the implementation to perform this kind of task.
So survey, you have essentially a survey data, right?
Right.
So let's assume the simple task is after the survey, you want to cluster your customers in terms of, or you want to know the sentiment of the customers, right? Let's assume sentiment if you want to get, or other thing could be you have a bunch of customers that you want to see what a basic question, who are your similar customers which gave the similar
Yeah.
feedback, right? So now so essentially what is that you are going to model here? You're going to model customers here. So imagine your queries could be like what Dinesh was showing. Every customer, you interact with every other customer. So let's say if you had survey from 100 customers, so every customer becomes, in terms of self-attention, every customer is represented, somehow you represent them by a vector. So one vector, every customer, let's say customer 1, you do a self-attention or a dot product with every other customer. So all 100 customers with a dot product. And then you get a weighted sum. Now that weighted sum will give you which customers are similar to the query customer that you have given me for your task. You getting the idea?
Right. Oh, okay.
So
And,
you have 100 customers. You have 100 customers. Somehow you represented them with 100 vectors. And now those becomes your, now you get a new customer. Let's say you get a new customer. You generate a vector for that customer. Now, and you have to tell this customer is similar to which customers or which part of which cluster. So you send this through your attention layer. You will get those attention weights. And then if you look at the grid, what Dinesh was showing, so imagine you have customers there instead of words, and you have that dark patches coming in. You can easily say this customer is similar to these customers.
Yeah, I mean, the previous one, this is not the one that I think he's referring somewhat, but the one with.
So a customer can have a very high dimensions, right, on which the survey being performed.
Yeah, so you pass it through the embedding layer, you reduce the dimensions. It's like the one-hot encoded analogy for a word.
Yep, you can have dense embeddings.
But though they are not categorical, they are maybe continuous.
It doesn't matter.
Value.
It doesn't matter. It doesn't matter. How you model them, it's up to you. So in this example, in this picture, if you imagine each of the rows and columns are same customers, and you have a task on which you have trained your model and you get these weights, then you can easily say the carousel customer is similar to carousel, which is definitely there, but A of front and in. So this customer, so whatever, let's say findings you have or promotions, if you want to give it to carousel customer, you can send the same promotions to, let's say, off, in, and front customers. Or let's say if you are giving some kind of discount or anything else.
I see. Okay, so here in case of NLP, we have the vocab length.
Yes.
There it may be the n number of the matrix, right? On
So
which
here word is the basic unit, which you
Right.
start with. There you have customer as the basic unit.
Okay.
So customer representation.
Mhm.
But again, like, I don't know, this should be solved via attention networks, because this is a very pretty standard for KNN clustering and self-supervised.
No,
And
but
that
you need to
would be-
learn the embeddings, right? So before you do clustering, how would you learn the embeddings of your representation? It's all
Yeah,
about representation learning.
Yeah, that was going to be done by feature designing. I was thinking like that would be much more, you can say, accurate. I don't know how embedding is going to, because that much sort of data to learn embeddings for customers, I don't know if it's available, then it's good. But
Exactly.
if it's
That's the
not,
prerequisite.
yeah, I mean, that much data from customers is like, I don't know if it's, I've not seen that state. So maybe,
And
The
another thing,
thought
it's
I was trying to put together Yeah, the thought I was trying to put together, there was an example in one of the paper about using attention-based mechanism in healthcare, right? In healthcare, we have the customers, the n number of, the medical data, maybe, different kind of procedures being performed. Now that if I try to visualize that something similar to what I had my use case of the CSP, right? So how exactly these things, this kind of use case is being solved using the attention-based models?
Yeah, so let me, maybe I can show you one example architecture that I built for one of the papers. I don't know, everybody is, if it's okay, it's already late, half an hour more.
Yeah, I think I will be dropping off.
Yeah.
I think you guys can continue. And really great presenting, guys. If there is any question, you can, I think, post it on the Slack channel related to my content and my explanation. I would be more than happy to answer them. Thank you.
Well, thanks,
Bye,
Dinesh.
guys.
This was really excellent. Excellent. I learned a lot.
Thanks.
I like the
Thanks, Ian.
complexity part, Dinesh. Maybe I'll pick you up. How did you test it?
Yeah, I mean, I took like whole evening to test it. So
Yeah, it's an effort taking talk. That's why I'm trying to reduce my effort. Right? Just
yeah,
cheating from you.
definitely. Yeah, I mean, you can have your self attention diverted towards that. So I don't know. So yeah, okay, cool. Thank you, guys.
Thanks.
Bye.
Thanks.
Good
Yeah.
night. Bye.
Okay.
Samarth, shall we continue?
Oh,
If you have
yeah.
time.
Yeah, I don't know. I mean, I have time, but I don't know about others. So, yeah,
Maybe if you could share some reference offline, I can go over it. If that's okay, and then when we connect next time, I can ask.
I have my paper. I think I'll just quickly show. Let me know if that's okay. What you're looking for, something similar, or if not, then.
Yeah, let's go over it. Thanks.
So this is how I enhanced a typical. This is an image processing thing, but it's not NLP. But essentially, I kind of enhanced this VGG16 pipeline, if you know, in image processing for, let's say, disease prediction by using attention modules, adding attention modules at every layer or different places. So if you see, this is, we chopped the VGG16 into different blocks. Like this is block 1, block 2 we call. And instead of last layer, we stripped off the last layer and we created these attention vectors at different positions and then concatenated it and then treated this as the last layer for prediction task. So this block, what you see, this attention module, what we called, you see it's like this. This is the design, essentially following the same thing, key, value, key, query, and value vectors. So so this is the entire architecture, right? For VGG16, this is the traditional architecture, layer by layer. And then you break it down into blocks, block 1, block 2, whatever blocks. And at one block, you take out, you treat every volume as a vector, key vector. So let's say if this is a volume, right? So this is a volume. So you can treat like, so let's say the volume is 2, 3, and 4, 2 cross 3 cross 4, or maybe not a bad idea, 3 cross 3 cross 4. That's the volume, right? So it's a volume thing. So you can remove you'll have like 4 3 cross 3 vectors. So in a way, every block becomes a key vector here. So essentially you'll have 9 vectors of dimension 4 each. So they become your key vectors. So I break this image into 9 vectors. The image is of size 4 cross 3 cross 3. So 4 is the depth, 3 cross 3 is your spatial frontal view. So you get, if you slice out every vector out of it, then you will get 9 vectors, each of dimension 4. So that becomes your key vectors. And then the query can be anything. Query is like which disease. So I have 14 diseases, let's say, or 15 diseases. So I'll represent each of these disease like anything. I mean, it could be just one hot encoded representation, and then you pass it through the embedding layer. So this becomes my, let's say, 14 query vectors. So essentially what I am asking my model to pay attention is what part of the image, what part of this X-ray image corresponds to a particular disease. So maybe disease 1 focuses on this part of the image, and this part of the image, and this part of the image, and this part of the image, right? So it is looking for certain traits in the image, and those traits can be in different locations. So maybe some kind of diseases happen only in the upper left corner of the lungs. So those kind of things. So it could be any kind of combination. It's in NLP world, it's like the source word, which are the target words which are firing or aligned with the source word. It's similar. So you just pass it through the attention mechanism calculation, take the combination, which is exactly what Dinesh was saying. You get out attention vectors, and that's what your attention output will be. And then you stick
in
this.
Dinesh case, before you move on. Yeah, in this case, the query vectors are your particular focus diseases.
Diseases, yes, diseases.
Okay. But what Dinesh explained, that was a random initialization kind of thing.
Yeah,
but
so this is also
this case,
random. This is random initialization of my diseases.
Okay. And now we are trying to map this.
So
Like
what we are
image,
trying to do here is we are trying to learn in a way. We are trying to learn which part of the disease vector is firing which section or which area of the image. Remember the grid, which on the rows you can have diseases and the columns you have image locations in a way.
Okay.
So you say which part of the image is firing for which disease, or which part of the image should the model pay attention for a particular disease. That's what the model is learning. So in your case, the keys, the customer example that you gave, right? So the keys will be customers, the queries will also be customers. Or it could be just one customer at a time if you want. So you look for customer 1 and which of the other customers are similar or this customer should pay attention to. Or let's say if you have some kind of a promotion, okay? So there you have 100 promotions, which customer should be mapped to which promotion, something like that. So it completely depends on your problem, how you model it.
Got it. At least I got now food for thought. I can brainstorm on that.
Yeah. And this is like, you can just push it like here we put this at different stages, because our hypothesis was maybe there are certain features which are learned by this traditional pipeline in the intermediate layers that would be good for decision making, versus by the time when you reach at the far end, you might have lost it, or maybe they are somewhere diluted. So what you do is you break it into smaller pieces, use attention, create those attention vectors, and then come up with the final representation that you pass through the linear layer then. So this is one way to apply attention. There could be n number of ways depending on your problem.
Very interesting.
Okay, so I don't know. I mean, just maybe for you guys, if I mean, Dinesh was right. You need, from data point of view, you need good amount of data, but you can even experiment with this reasonable size data. I think it should work in my view, if there are good patterns and you don't overblow your representations. And this comes with explainability as well. So your features, the vectors that you match, those are kind of sometimes give you the features also, which features are more important. So in image case, I could project those regions in my image which fired a lot, and then I can blur everything and just make the other one more high. So any doctor can see and say, okay, look, when my model is saying this belongs to XYZ disease because it spotted something in this region of the X-ray or the image, and you can highlight that region. So it gives some kind of interpretability as well. Don't know if it makes sense or it helped, but
To some extent, yes. But I think I have to learn more to get, to your frequency and the way you are explaining. So
yeah, it
yes.
takes some, you need to sit quietly and write down on pen and paper to see how things are moving around. But if you do, you'll get, it's not that complicated. It takes time. I mean, I agree. You need to really be patient and sit down in a quiet room.
Probably, yeah. Thank you. But it definitely gives some thought, to explore in the particular direction.
Hey, Ilya, you joined?
Oh, I'm here in the background. I'm not actually participating today.
Oh,
yeah.
okay. I thought, okay. No worries. Okay, then, chalo, I think.
Thanks, everyone.
Thanks so much. Thanks a lot. Bye.
See you next week. Bye.